Okay, we got that rolling. So now, go ahead with your with any questions.
Okay. So my first question is number 12 on the pretest. Is that, where was it? Hold on. So is that one false because the first one's false?
It's actually not false. It's true. And it's true because the first statement is false.
That's what I meant. Okay. Okay. So if the first statement is like, so if we get a question like this on a test and we see that the first statement is false, but the second statement is true, then it's true.
Yeah, in fact, we can even be more general. If the first statement is false, it's guaranteed to be true.
Okay.
You don't even need, ironically, then you don't even need to know the value of the second. Because if false, then true, true. If false, then false, true.
Oh, okay.
So, yeah.
Okay. And then number 18, I had a question.
On the practice test?
Yes. So would I have to do like a truth table for all of them, or?
Yeah. Right. That's the idea. You got to, when they say which of these are tautologies, it could be one, it could be all of them. It could be two of them. So yeah, you need a truth table that takes a look at all of them. So you notice question A, I did in this column right here.
Okay.
Here's where I did B.
Okay. And then C is the last one.
C is the more complicated one there. Yeah. So yeah, when a question is asked in that way, you really need to check them all, and you can put them all in one truth table like I did.
Okay.
And the answer?
B. Yeah, B.
Yeah, only B. In this case, only one of them turned out to be a tautology.
And then, sorry, I'm taking up all the questions here. So for the, extra credit. Now,
yes.
If I have a truth table, like for example, this one, let me just like say I have, a truth table for this one. Can I say something like the statement, or like, can I say like question or problem B is the answer because it's a tautology, or how would I go about?
That would be pretty good. You might, yeah, or you could just say of all three statements, only B is, or something like that. And because you could be writing here forever otherwise, explaining to me how you did P and not P, and So here I would just, when you have a multiple choice like this, just say, all right, I tried all three of them, and only B works.
Okay, so let's say I don't have a multiple choice one, but I like have a truth table question.
Yeah, let me see if I can find one here.
Okay.
Okay, so like maybe number 13 here.
Yeah.
So what would be a suitable extra credit for that problem? Well, I think I would just say, all right, here's what I'd write. First of all, there are only 2 letters, therefore I needed 4 rows. For the if then, The only statement that's false is when the first one's true and the second one's false. And for the Q or not P, it's an or. There I use the rule only false when both are false. And then for the last thing I had to do, the if and only if, they're only true and they're alike. And I don't know, maybe something like that. I don't know.
Okay.
It doesn't have to be that way. I'm just trying to give you a sample. So because...
Could I give you the answer for that one, like written out, or did you want me to do something like how you? Like,
what do you mean? What do you mean by the answer?
So, like, could I say something like, well, no, that wouldn't make sense because then how did I get the answer? That's the thing. Okay, never mind.
You'd have to have the truth table somewhere on your paper, and then, yeah, and then words. Maybe you don't have to have as much as I gave you, but by the way, don't overlook the fact that the number of rows can also be described. So if you had a 3-letter problem, you'd have to have 8 rows. You know what I mean?
Mm-hmm.
So that looks good when I'm deciding on how many points to give.
Okay. Okay, I'm just gonna try my best to do the extra credit and hopefully
and there's really no one correct answer, but if I deem that you made a good effort at explaining what you did and not just, oh, the answer is here.
Mm-hmm.
That's not enough. The answer is right above my arrow. No, that wouldn't be extra credit. You got to do more than, you got to do a little bit. You got to do more than that.
And those are only good. So, like, for example, for like the, I'm just pulling this out. Like, let's say on the pretest, where 7B, for example, where it's P or I'm sorry, or 7A, one of those, like the ones that don't have, like, could I say something like P is, greater than, I'm just throwing this out there. P is greater than or equal to the Q. Could I say something like that for A, and then like B, could that kind of thing, or does that not count as extra credit?
Would you say that again?
So, like, if I were to write out, I'm just gonna throw an easy one there. Like, if I were to write out 7C, like, and explain it, could I just say 7C is negation P, or no?
That would be enough. Sure. I mean,
or like
maybe you should just go
Q or P or Q, that kind of thing.
Maybe you should just go a little bit past that and say 7C, negation P because all the entries are the opposite of P.
Okay.
Something like that.
Okay.
Instead of TTFF, FFT, just all the entries are opposites.
Okay. Sorry, I just want to make sure I have this down.
I'm glad you're asking. I know it's hard to get a feel, but I think it's good that we're having this discussion. Gives you a better idea.
Can I ask a question way back on 3.3? I went back and tried to redo some of the problems.
Okay, go ahead.
3.3, number 53.
Got it. How about that? All right. Now, I do need to look up. Let me look up the actual statement of the problem. 53 and 3.3.
3.3.
So the directions here are what? write each statement in the if-then form. No, I guess this one's just on its own. So, if you eat the spinach and the liver, then you may go out and play. So I wrote that as spinach and liver, S and L. If that, then play P. So the question is, the child eats only the spinach. That means the first part of the statement is going to be false because the kid did not eat the spinach and the liver. So that's it. That's this writing right here. Get my pen. That's this. So he didn't eat spinach and liver, and she still let him go out and play. I don't. Why did I put T? I should have been a P there.
I was really trying to figure out how we went from the S and L to the T and F.
Yeah, I mean, okay, what that meant was true. There's one of the statements in the S and L was true, and the other one was false. So he did eat the spinach, but he did not eat the liver.
Okay, so you were just saying true.
True and false.
Okay.
And so the first part, because for and they both have to be true to be true. So the first part of the statement is false. And the second part is true because she let him go out and play. So what would you evaluate if F then T? So now go to your rules of if then. In an if then statement, that would be true.
I don't know what I was thinking. I did.
So anyway, Mom didn't lie.
I don't know what I was thinking. I did true. I tried to do a truth table on it, so I don't know what I was doing. You just looked at the components.
A truth table might have been a good way to do it. But anyway, this is what it comes down to.
Okay.
The beginning part of the if then is false, so it's like guaranteed to be okay.
Okay.
Yeah. Okay. So what it amounts to is Mom, in her promise or her statement to the kid, never talked about this situation. You know, she said, if you do both of them, I'll let you go out and play. She didn't talk about what she'd do if they didn't do one of them or didn't do both of them. That's what it comes down to.
And I think that's what threw me off too. Like, because I was expecting it to be like, I don't know, like hers, like if you don't eat, you know, your spinach or whatever, then you don't go out to play. Like,
yeah, I get that. That you're right. That's a flaw that most people have. You know, Mom says, if you eat your spinach and liver, I'm going to let you go out and play.
Right.
Which kind of sounds like if you don't eat those two, you're going to sit here and rot until you do.
Right.
But that's not what she said, you know?
Mm-hmm.
So most people assume the opposite like that. And anyway, this is the reason it's a truth. She did not lie.
Okay. Would you mind looking at number 55 then again?
On that same lesson?
Yes. Right below it. Yep.
Okay.
I wasn't sure how to go about answering it.
Let me find some space here. See, maybe I can fit it in here. Okay. So this is 3.3, number 55. Okay, let's find it. So which of the following statements is logically equivalent to if Mary is in Tampa? So I'm going to just write that this way. If she's in Tampa, then she's in Florida. Okay. So now which of the statements they give us are the equivalent to that? So I'm going to try writing those out. So here's A. Mary is in Florida or she is in Tampa. Okay. B is if Mary is not in Tampa, then she is not in Florida. C, if Mary is in Florida, then she is in Tampa. And D, if Mary is not in Florida, then she is not in Tampa. So I don't know, does that help you look at them?
It'd be the opposite.
Can you already see D is good?
Yep.
Because it's the contrapositive?
So that's what I had. I just wasn't sure.
Now, hang on. There might be another. No, there isn't. But had they given this for an answer, do you remember that? Based on that hint, that would have been okay too?
Mm-hmm.
Remember that famous hint, number 23 on that one page? So they didn't, but so D is the correct answer. Chris, are you with me on that?
I think so.
Still have questions?
I think I was trying to do more with it.
Okay.
Being that I see it now, as you just laid it out in a row. I had them I was trying to make the contrapositive of the statement each time, which wasn't making any sense. I was saying F or T, and then I was doing the contrapositive of that. And so I had too much, and I didn't know where to go with that.
Yeah, just a comment. You can't take the truth, but the way it sits, you cannot take the contrapositive of A, because in order to take a contrapositive, you have to have an if-then.
Right. I was doing that.
Okay.
And it didn't make any sense.
Okay.
That would be why it wasn't making sense, but I didn't know why it wasn't making any sense.
Yep.
Okay. And there was one other section that I had a bunch of question marks on. And I know it goes back to writing the sentences. I can't, for some reason, I get them backwards all the time. Section 3 in chapter 3.4, number 31, I was able to write the statement okay, and then it says true, and I can't wrap my head around why they're saying it's true.
Okay, let me find some space.
So it's 3.4, number 31. I'm not sure why when they make the statement that it's true or false. I'm not sure I'm understanding why they're saying that it's true or false. If that makes any sense at all.
Okay, 3.4. Go to that lesson. Number 31. So if an integer is even, then its square is divisible by 4. So in other words, if you take an even integer like 2, 4, 6, 8, and you square it, will it always be divisible by 4? Well, that's what we got to think about. So let's think it through. Well, 2 squared is 4. That's 4 is divisible by 4. 4 squared is 16. 16 is divisible by 4. 6 squared is 36. That's divisible by 4. 7 squared, I'm sorry, 8 squared is 64. That's divisible by 4, which is 10 squared is 100. Yeah, it looks to be, I mean, from what I can just see there, that seems to be true. So there's a case where you just have to try a whole bunch of them and see. You can't test everything. But I might go a little further. All right, what's 12 squared? 144. Is 144 divisible by 4?
Okay, so the reason I had trouble with that one is because we have not been reading the English words literally. They've made no sense. Sometimes they're kind of far out there and they don't make sense. So even though I understood that the math was right, the integers, even the square is divisible by 4, that seems simple. But nothing else, all these other phrases.
I didn't follow the directions. Okay, the directions are, I was supposed to write the converse, wasn't I?
Write the converse, right. Yep.
Hey, I haven't talked about that. That's what you call jump into the problem and don't read the directions. Okay, what's the converse of that? The converse is if the square of a number is divisible by 4, then the number must have been an even integer.
Right.
Okay, now I got to think about that one. So, for example, how about this one? Let's say the square of a number is 12. Yeah, I know you're probably thinking that that doesn't come from an integer. I got to think about that. So, if the square of a number is divisible by 4 and 12 is divisible by 4, then it must have come from an even integer. If a square is divisible by 4, so I suppose here's the problem with this one. It all depends on, I mean, I could say the square of an integer is 12, and that's divisible by 4. That doesn't mean that the square root of 12, which is what we would have to number, was an even integer. But that's a hard one, because when they say the square is divisible by 4, are they saying the square of an integer is divisible by 4? I think that's kind of implied. So
Yeah.
I'm guessing this is true. What did the book say?
That's true.
Okay. Yeah. And so anyway, you see what I just thought through? So if you just take this as, if a number squared is divisible by 4, and technically that could be this one, 12, and that's divisible by 4, then it must have come, then square root of 12 must be an even integer, and it's not. But the problem is, it's kind of implying it's the square of an integer. The converse is, if the square of an integer is divisible by 4, then the integer is even. Then it's going to be true. So that one turned out to be deeper than I think they intended. That wasn't supposed to be that hard, but.
Okay, so in that same thought process, can you do number 33? Because I wrote the sentence okay, and then it said false in the back of the book, and again I went, why?
Okay. So if it's raining, then there are clouds in the sky. The converse is, if there are clouds in the sky, then it is raining.
That's
number 33.
Yeah, number 33.
33.
All right. In order to get a date, I must be neat and well. Oh, okay. But before you write a converse, what's the original statement?
If, in order to get a date, I must be neat and well dressed.
Yeah, I mean, yeah, but in order to do a converse, it's got to be an if-then form. So can you write that statement in if-then form?
If I am neat and well dressed, then I will get a date.
Yes.
Mm-hmm.
And the converse of that is, if I get a date, then I must be neat and well dressed. Or to get it, you know what I,
Yeah.
because I just took your if-then form. So let me get this straight.
So why is it false?
Well, okay, because a converse is always questionable when you flip it around, isn't it? Think about it. I mean, unless it's a biconditional, if you flip it around, converse is what's the only thing that's equivalent to the original? A contrapositive. So converse is going to be I'm very skeptical. Now, here's what it says. If I'm neat and well dressed, then I will get a date. The contrapositive is, if I get a date, then I was neat and well dressed. And yeah, I don't know what to tell you, except converse is always questionable. Except why did it work on number 31? Because that's actually a biconditional. Yeah, that's a tough one. But I'm skeptical of all converses because you remember converse is not the same as the original.
Right.
So that would be the first thing I would say. Yeah, 34 is a lot. 34 is a lot easier to see that on.
Okay.
You know, if M is elected to office, then all our problems are over. So, if all our problems are over, then M must have been elected. No, it could have been another nice guy named P. I don't know. How about 35?
If you pass this course, then you get passing grades on all the tests.
Okay. Now, but that's not how it reads.
Oh, I was reading you my answer. I'm sorry.
No. All right. So, what does sufficient mean? That's the if part.
Sufficient. Yeah, sufficient is if.
So the if part is really, if I get passing grades in all the tests, then I will pass this course. That's the statement. Now, what's the converse? If I pass this course, then I got passing grades in all the tests. And that's not necessarily true because, you might have gotten A, F, and you passed the course.
Mm-hmm.
But, so again, a converse is highly, you should always be skeptical of a converse. 31 turns out the converse works, but that means that if the converse worked, then it must have been a biconditional, even more than what they gave in the beginning. So I'm not going to ask you to write any converses. I can tell you.
Thank you. Thanks for showing that.
But well, I mean, yeah, but I'll be honest. The hardest part about writing a converse is getting the statement right in the first place.
Yes.
And when you start with, in order to, boy, okay. You got to look at it and go, wait a minute, what's the if part and what's the then part? And then write it out. If this, then that. Now switch the if and the then, and then you got a converse. So, and then there's a key, and when there's a key word like sufficient to number 35, that tells you which thing is which.
Okay. Okay. Thank you.
Yeah. So Marilyn, we're into questions. We're doing questions first.
Okay.
You're welcome to ask questions.
Okay. Okay. So if we're doing negations,
Yes.
so negations can be conditionals, and or doors or anything. Would you ask those any particular way like that? You know, like an and or statement, a conditional. You follow me? My question?
Yeah, I'm trying to get the full, all the implications of what you just asked. You're saying I could ask for a negation of anything.
Right.
That's actually, it's actually pretty good. I mean, I like that. And I'm going to let me show you some examples. Get some space here. Change the arrow. There we go. Okay. So like if I gave you, well, I suppose we could do it in words or symbols. Well, I'm going to try it in symbols first. So if A, then B. So what's the negation of that? Oh, what's the only time? What's the only time an if then is false?
When the first one is true and the second one is false.
So you could say that, and this is the negation of that. Let me put it off to the right. Sorry. Yes, you are correct, Marilyn. So what I wanted to do is this. So let's just write negations over here. So the negation of if A then B is when the first part is true and the second part is false. So this is the negation of that.
Okay. Okay.
Let's
well,
go ahead. Let me just show you some others. Now this one I think you know. What's the negation of an and? This is a this is a famous
negating
Compliment?
like a De Morgan's or
yes, Marilyn.
okay.
So therefore this one is not A or not B.
Okay.
And then if we had an A or B, just because of De Morgan again, it would be not A and not B.
Okay.
Okay, so yeah, you're right. Just about any sentence I might ask you, or I might ask you for negation, and there's some guidelines there.
Hold on, don't erase that for just a minute. Let me just copy that.
Okay, so the I think the reason why that question came to mind for me was because when looking at how to negate some things, and it just wasn't clear why it seemed like the first statement would stay the same. And those were the conditional ones. So a statement like, if I go to church, then I will be a better Christian. Okay.
Right.
So the negation of that being a conditional would be, if I go to church, I will not become a better Christian.
That's correct. That's correct.
Okay. Okay. So I guess where I was coming into the problems was not really recognizing when I'm trying to negate, if I'm negating a conditional or.
By the way, that was a very good insight, because a lot of students, if they want to negate an if then, what they almost automatically do is negate the first.
Negate both of them. Yeah.
Or
negate both.
Yeah. Well, that or they'll But the point is the A doesn't change, and
right.
That's a common mistake.
Okay. Cool. Okay. Okay.
Well, I just want to make this general comment. I can already tell you guys have been studying because the questions are of a much higher quality. They're really, you guys are asking good questions. I mean that. You're asking good questions. I like that. That shows you're being good students.
Okay, so then another one on negation. I think. Wait a minute. Okay, now I know you said that I was popping out by asking, by putting it is not the case in front of okay, I guess it would be like excuse me, an and statement.
Okay.
So if you want to negate an and statement, by just putting, okay, so let's see, let me find one. Okay, just say A and B. It is not the, if you want to negate that, it is not the case that A or B.
Well,
Maybe I'm not saying
right.
that.
Yeah, you just say not A or not B. You want to have the not on the B too. You know, you say not A or B. It's a little hard to tell if you had the the A or B in parentheses or not. So
Okay.
but that actually that's this thing in the black ring up here. Yeah.
Right. Okay.
So if I said to you, I'm going to come to class and I'm going to be there early, what's the negation of that? When did I lie? Well, if I didn't come to class, I would have lied.
Mm-hmm.
Or if I didn't come to class early, I would have lied. So you see, so
yeah. So then would you say that I did not come, it is not the case that I came to class early, or what was the other part?
I came to class.
I came to class, or I came to class early.
Right. You don't, I would stay away from that. It is not the case.
Oh, really? Okay.
Yeah, because, I mean, you haven't really done anything. You're just saying, oh, it's the opposite of this, but I don't quite know what, you know what I mean? It's not specific enough. So,
okay. I think I just saw some answers in the back of the book like that, and I was just wondering how they came into play.
Yeah, I would encourage you against that because that leads away from understanding.
Okay.
Yeah.
No problem.
So, how are we doing? Did you have any other things you'd like to talk about?
I probably wouldn't talk to you for another 2 hours if I had the option, but my brain is getting scrambled. So
Okay.
I just keep trying to keep doing them, and that's all I can do.
Well, yeah, we don't want scrambled.
Scrambled.
Maybe over easy we could deal with, but I don't know about scrambled.
I think I'm overthinking a lot of it, and then I confuse myself. So I'm just going to do the retest again and see what I can do from there.
Okay, I get you. You're right. I think that is happening with in some cases. That's easy to do in this chapter. Well, should I do the presentation and we come back to questions, or does okay? Go ahead.
Okay, good.
Okay, so let's see. Our first chapter was we used the two infinities, and it was part of this divine design. Okay, this is one of my all-time favorites, called "Thinking God's Thoughts After Him." And if you look at the what's on the screen here, you can maybe give me a couple ideas what you think that might be. I'll give you a clue. If you look at the outside of the picture, you notice something about that might be a clue. You know, outside the circle, what does that look like?
Switching networks.
Yeah, yeah, or a chip. Yep.
Yep.
It's electronic circuit board. Exactly. Well, what's in the so let me just tell you what this is. When some people are born with bad retinas, and those retinas, although they can see, it can see very little. So what this is this is an invention of a man-made retina, and they've used this to implant it in some of those people, and those people have been able to see at a much better rate. Anyway, and you notice they made this thing. They even copied God's design. I mean, it's round, like a human retina is. And
I was gonna say it was an eye, but I didn't want to be wrong.
That's basically the idea. What they did is they created a retina, and it's not too surprising they copied God's design for the eye, at least to a certain extent. And it's worked quite well. It's actually made people have enough vision to live their lives without being blind. Okay, so the idea of this presentation is God has these incredible designs in his creation. And, well, anyway, the idea is copying those thoughts. So here we go. So in the beginning here, I have some introductory slides to get you warmed up a little bit. This is a fact. Not too long ago, I guess, depends on what you call long ago, but before the Gulf War, the United States Air Force came up with an idea for a new ground speed indicator. Triple the accuracy for ground speed than the previous one. And you think back to the Gulf War, I remember watching it kind of live? That was weird, watching a war live. But they showed human jets sending a munition toward a building, and not only hitting the building, but hitting it right between the two front doors. And anyway, this invention is what allowed them to do that. But now here's the part that people didn't hear. Where did they get the idea for triple the accuracy? Where did they get the idea for that new technology? This was not put in newspapers, so I don't expect you to know. So I'm going to tell you. The beetle. This guy, in fact, they observed this insect, and he's got a device off his head, and he's got one off his tail, and he does this timing thing. The Air Force copied it, put it on its jets, and the jets immediately were better technology. Okay, so that's kind of and by the way, these are the jets that it's on. It's the same jets that I don't know if you've ever seen the Blue Angels.
Yes.
But it's on those jets. Okay. The best lubricant known to man is being studied so we can make better use of it. If we could know that, my goodness, we could make our car engines last forever, you know, it would be awesome. Where is the best lubricant known to man found? Any ideas?
As in like a country or?
Well, I mean, in what object?
Water.
That's a good guess. Water has some lubricating factor to it. That's true.
Oil?
Yeah, oil, gas.
Closer.
Gas.
Well, Yeah, it's a special chemical, and guess where it's found? It's in you.
Oh.
In fact, it's basically the chemical that's in your joints. And when that's not at peak efficiency, we call it arthritis. So check that out. With all the high tech we have, isn't it wild that the best lubricant found that we know today is actually in a creation of God? Okay. Oh, I went the wrong way. There we go. All right. We're always trying to find ways to get better aerodynamics for flight. So how can we shape a plane so it kind of slips through the air better? Because if you can make jets slip through the air better, they're going to be safer and they're going to be more efficient, use less fuel, all kinds of good things. So where do you think we're finding answers to how we can do that better? I mean, it's pretty obvious. You probably
Birds.
look at anything flying, right? Yeah. Turns out that birds are certainly part of it, but the dragonfly is really on top of it. The dragonfly has two sets of wings, and just think of a hot summer day, and you're by your house by the garden, and a dragonfly comes, and you know how they just dart, they just turn immediately. Can you imagine if our aircraft could do that? I mean, we'd be able to fly circles around the opponent. And guess what? The government's actually looking into that. Why is that, and how can they copy it? But now, this second thing is going to surprise you. Yeah, I actually mean a blue whale.
What?
Yeah. Let me explain. Okay, this is the largest mammal on Earth, the blue whale. And he too has this maneuverability. It's a thing that allows him to slip through the water really efficiently. And he looks like a kind of a chubby guy, but he really is very efficient at sliding through the water. And if he can slide through the water better, maybe planes could slide through the air better. That's the idea. Okay. See if you know this one. What high-tech arm is in use? The first one cost $100 million. Well, I'll tell you. It's that arm on the. I know we don't think about the shuttle anymore, but here's a picture of the space shuttle, and you see that arm coming out of the dock that was made by Canada.
Yep. Awesome
Technology. And by the way, we've got a copy of that on the space station now. But here's the thing. Awesome. It worked just like Canada did an awesome job designing it. But guess what? When it came back to Earth, it's useless on Earth. It's specifically designed to work in that weightless environment, and it works beautifully. But when they come down to Earth, it's like this it's like a useless piece of equipment. Okay? Last I checked, when the astronauts came back down, they were able to still use their arms in both places. Okay, and you're starting to get the idea here. Scientists are now studying a computer which is so powerful, we've only been able to imagine such computing power. What is this famous computer called?
The human brain?
You got it. That is correct. Okay, so you got the idea now. That's kind of the theme of this presentation. The whole thing, again, is called Divine Design. And this particular one is called Thinking God's Thoughts After Him. Okay, so to get started here, now that we've had our intro, I mean, this building was built, 4,500 years ago? It's the Great Pyramid of Giza. Obviously, these guys knew a lot about mathematics because, I mean, there's 2.5 tons. Each stone is like 2.5 tons and is designed in a block. And it's designed so precisely that you can't even slide a piece of paper between two. And it's all tooled by hand with, I don't know, some kind of stone chisel. We don't know. But what's going on here? They obviously knew something about math. And when you go to Central America, the Mayan pyramids are also very precise. Another picture of the Mayan pyramid. So the question I want to ask is, what is mathematics? And how, how does it allow us to actually figure things out so precisely? In God's creation, they mimic, a lot of mathematics is mimicked. Like, for example, if you think about parallel lines, it's not too far to see. I mean, you can see parallel lines in these stalactites. You can also see it in something as simple as palm fronds or crystal edges, or even if you have a straight line with a, with a spider silk. And if you ever have a chance to fly in an airplane, sometimes you'll get a view of the sunlight that indicates this idea of straight lines. Or here maybe is a better picture. If the conditions are right and the light is coming down. So obviously this idea of a line came from God's creation, or even rain falling. And when you talk about flat surfaces, I realize we don't live on a flat planet, but for small ponds like the one you're looking at there, I mean, we would call, especially a calm pond, we would call that pretty doggone horizontal. In fact, it's how we make our levels, isn't it? Mm-hmm. What do we do with a level? Well, the old levels, we used to put a little air bubble inside a chamber, and when that bubble was in the center, we would know that we had the thing level. If you take little skeletons like this and dip them in soap solution, the soap solution right away knows to go to it goes to this configuration that you're looking at. You can get a feel for that. And that configuration, I'm not joking, holds the maximum amount of inside material for the minimum amount of surface area material. Now, normally, in order to find maximum and minimum, you got to be able to do really high-level math called calculus. But God, things in God's creation seem to do that automatically. Here are just some crystals. Notice how beautifully straight the edges are on these. These are wolf and beetle crystals. Here are some aluminum crystals under a microscope. Okay, now let's move to circles. You get the idea that God uses a lot of circles too. When you take any kind of a tree and cut it, of course, what do you see? You see a bunch of growth circles. Circles are a big part of creation. Here we see the eclipse of a planet. Here we see, oh, that's right, rainbows are based on circles too. And every once in a while you can see a complete half circle like this one. And, oh, there's so much precision in there. The red is always makes a certain angle with the sun, and the green makes a precise, every color. Yeah, I don't have time for that, but getting back to the circle, we see it after a rainstorm. Water droplets are spheres. You see another picture here. And I mean, when a droplet hits a water pond, it makes all kinds of mathematics. So you look at a picture like this, and we can, thanks to our space program, and you realize, holy cow, there's a lot of math around us. I mean, we live on a spherical object. Or you look at this picture. I mean, how can you not see mathematics here? It looks like God took out his compass, and in a way, he did. So even the sun and the sunspots are also circles. This is one of my favorites. If you take a camera and go to a place like Alaska where they have longer night in their days, and aim a camera at the North Star, put it on a tripod, and go away for about 4 hours and just let the shutter open. This is the result. In other words, we didn't turn the camera. This is God spinning the earth on its axis. So every day, the earth makes these circles because we spin around on our axis. Okay, if you take a bunch of circles and put them on another bigger circle, and you kind of crowd them in like happens here. Oh, I missed something. So first of all, insect eyes are made that way. Do you see how that's the insect eye? And do you see how there's a bunch of little spheres making up that eyeball? Yeah, if we can do that mathematically too. We can take a sphere and plug those in. But when you crowd them a little too much, and if you take a close-up, look at what you get. They immediately go to six-sided hexagonal shapes. And there's a lot of mathematics in that too. How about this? Just take a fountain and let it shoot it up in the air, and what do we have? We have a parabola, which everybody studies in high school algebra. It's the shape of gravity. Here you can see it again. This is a guy doing some grinding, and you can see all the sparks. All those sparks are a mathematical shape called a parabola. Here you see it on a volcano, an active volcano. You can see the streaks, those same mathematical shapes. Okay, so now we want to take a little time with the dragonfly. We spoke about him in the beginning. One of the things that makes the dragonfly so good at maneuvering is he has two sets of wings, as you can see in this picture. And you can see that one set of wings is up, the other is down, and you see how balanced it is, left and right. Well, because these things are so maneuverable, we decided we're gonna take a close look at this. Our Air Force, our government, actually took dragonflies, put them in little tiny wind tunnels, and threw wind at them, and measured the airfoils. You know, how does the smoke go over? You know, how do the wings work?
Poor
Works well. And you can see we've got digital readouts here. They're studying this very closely. Sometimes really cool aircraft result, like this vertical takeoff and landing jet. This jet can take off straight up and down, and then it can fire off like a regular jet. So here's that blue whale again. Okay, so on the left, we have a crack flying team, flying in formation. On the right, we have a crack flying team, flying in formation. And you know the source of the one on the right, of course, that's God's creation. Interesting thing that NASA found when they studied flight of birds like this. They found out that when birds or planes fly in formation, they use less fuel, and it saves energy. And looks to me like God got that message across to the birds long ago. Here's from an old magazine advertisement. She, the spider, is teaching us how to build a safer parachute. The spider silk is an amazing material that we are currently trying to study and copy. Here's why. When you land a jet on an aircraft carrier, you've got a really serious problem. The runway is way too short. Okay, and so you know what they do? If you look real carefully, you can see where my mouse pointer is. You see that cable there? Across. Actually it's a pretty doggone big steel, incredibly strong steel cable, and it catches on to this arm that comes down from the plane, and it just literally pulls on and stops the plane when they land. Okay, now it's like 3-inch diameter. I mean, this is really a big cable. Okay, well, if you look at the top, if you use that as the size of the cable on the left, the wound steel cable, spider silk is so strong that you could use this size if you use spider silk. And I know you're saying, what? Spider silk could stop the plane? Spider silk 5 times stronger than steel. See it on the bottom there?
Wow.
And to top it off, it's got flex. It's really an amazing material, and they're trying to learn more about it. And guess who the design architect was? Yeah, that was the Holy Spirit. That was God when he let there be. This gentleman is a professor at the University of Wyoming, and he's been studying spider silk. And they're trying to find the secret. They're trying to make a man-made. I mean, it's hard. It's hard to collect spider silk from real spiders. There's not that much. So they're trying to find a way to produce something a lot like it. Well, he's gotten pretty close. And he said, when you finally get to that point, it's like, at this moment in time, God and I are the only people who know the answer to this. Really cool. An admission of a nice confession by a scientist. You don't hear too many of those. Why do we want to know about things like spider silk? Well, how about when we use things like cables to suspend bridges? Or we even put trucks and so forth on parachutes. There's our friend the Beetle, where we got the ground speed indicator from. Now, look at this. McDonnell Douglas, United States company that produces many aviation designs. And I don't expect you to read it all, but the whole idea is those Hornets, the Hornet is the name of that plane that lands on aircraft carriers. And notice the title, Breakthrough Lets Hornets Land Like Grasshoppers. The idea here is the grasshopper has this incredible spring tension in its legs. You can see that on the picture. And the idea was they actually copied how the grasshopper's legs work, so that when this plane hits the deck, it has to come down really quick, and it hits that deck with incredible force. It better flex, or we've got disaster. And look, here we got a airplane manufacturer admitting, okay, we copied Guide's design for the grasshopper. All right. A new mathematical theory of insect flight could help engineers copy flies' tricks. You know how hard it is to catch a fly, right? Or to kill one. Oh my goodness. You can swing about 50 times and miss. Well, they're actually developing research on how these things can do that. Well, you talk about a really cool technology. Hey, how about walking on water? This is a picture of a water strider. It's an insect that literally knows how to stay above water, and it does. And this is kind of cool. I got to show you this video. Here we go.
Some young Costa Rican basilisk lizards are looking for food. Basilisks have been nicknamed the Jesus Christ lizard. Why? This adult male, probably the father of the young lizards, can't tell us. Nor can this female, exclusive property of the territorial male. It has nothing to do with the feeding habits of the basilisk, which consists primarily of insects and berries. This predatory reptile will help reveal the secret as it stalks the young basilisk. The basilisk is called the Jesus Christ lizard because it can walk, well, really run on water. It bicycles its hind legs, and the tail becomes a counterweight. We can't know what the snake is thinking. Did it really want to eat the lizard, or did it just want to show?
By the way, I've read a little bit about that, and we could actually run on the top of water too, but we'd have to go approximately 80 miles an hour to do it. Isn't it clever? That lizard is actually called the Jesus Christ lizard.
I kind of had a feeling with the name, like when they first said it, I was like, I have a feeling that they can do something like walk on water or something.
Yeah, that's exactly what they were intending. Yep. Okay. So now, if you look at the globe and you look at that tiny little green dot that arrow is pointing at, that's halfway between South America and Africa. That's Ascension Island. Ascension Island in World War II was very important. That's where our planes would stop to refuel. You could not fly over the entire ocean at the time of World War II. In fact, they had not invented mid-air refueling at that point. So, to get over there, they had to find this Ascension Island. I mean, if you couldn't find the island, you were literally up the creek. In fact, here's what the saying was: if you miss Ascension, your wife gets the pension. I mean, that's how serious it was. I know a little bit about this because my dad was a navigator in World War II. And boy, when they got over the ocean, they got real nervous. I remember, he would say, they would ask him if he wanted coffee or whatever. That would not be a time for a navigator to take a nap. So how in the world sea turtles know how to make that same trip underwater? We don't know how, but they make it with pinpoint accuracy. How do we know? We've tagged these turtles, and they make that trip. So what's going on here? We don't know, but there's technology there that we don't know how it's done. So here's a picture of a bat. The reason I'm showing you a bat is because bats use sonar. I don't know if you ever tried to catch a bat, but they can sense right away where your hand is by sonar technology. Dolphins also have this ability to communicate by sonar. This is, okay, I got to remember. I got to look. This is a horseshoe crab. Okay, and a horseshoe crab has the ability to sense light when it's extremely dark. It actually has eyes at those locations, and including that like stem that comes out on the right there. It can sense light and it like totally dark. And anyway, here's the cool thing about this. If you look at one of the eyes of this, it looks like this. And from that eye came the idea for some of the best TV resolution. So chances are we have a TV at home that uses technology from the horseshoe crab. And most people don't know about that one either. I'm going to tell you a little bit about the abalone. It's really a very, very hard shell. The picture on the bottom right shows how it's actually like brick, where the parts of the structure fit together when you look at it under a microscope. So, University of California molecular biologist Daniel Morse worked for 5 years to crack that, to figure out how the abalone gets this hard surface. You can see, he says, an abalone can withstand assaults from a hungry sea otter, pounding on its shell with a rock. And I love this second part. Such tremendous strength made us realize that nature has already solved
Engineering
problems. Did you know this? 1948, Swiss engineer George de Mestral. He's walking along and he gets all these cockleburrs in his socks, and his dog had them all over, you know, those burrs. Really irritating. And he turned it into a positive. That's where the idea came from for Velcro. And
oh, look at that.
all he did was copy how those cockleburrs work, and sure enough, he's got, you know, Velcro. Okay, that's a rat, and that's a saw blade. Let me explain. Rats' teeth have really cool technology built into them. Here's how it works. On the outside of a rat's tooth is very hard. It's almost like a ceramic. The inside of their teeth is actually very soft. So what happens when the rat bites on things is the soft part wears away, but the ceramic part stays there, and the net result is the teeth always stay sharp. And guess what we're trying to do? We're trying to copy that, because if we could make blades that stay sharp all the time, we wouldn't have to replace them. We wouldn't have to sharpen them. What do you think is the best adhesive? Super glue. Yeah. Duct tape. We definitely need, you know, college campus. That gets a big vote. Would you believe gecko glue? Actually, it's coming out. Have you all had a chance to see what geckos can do? They can walk up glass. They can, you know, they can hang upside down, and they inside those little fingers that they have are all these little setae, which they try to show you in that circle down at the bottom there. Anyway, amazing how they can hang on to things. So here's how it ends up. Engineers that are studying, they're studying these things because of the cool technology. And look at what the scientists said. Engineering a structure as exquisite as the foot of a gecko is probably beyond human technology. So here's where I pause, and I use this passage from Job chapter 12. And I think you'll get where I'm coming from here. But ask the animals, and they will teach you, or the birds of the air, and they will tell you, or speak to the earth, and it will teach you, or let the fish of the sea inform you. Which of all these does not know that the hand of the Lord has done this? In his hand is the life of every creature and the breath of all mankind. That passage has a lot more meaning for me after looking at some of the stuff we just looked at. This is a cottonwood tree. And let me explain why I have this picture up. You aren't going to believe this, but it's true. So a grove of cottonwoods is just this picture, this grove of cottonwoods outside of a town. And all of a sudden, a predator insect is coming to basically destroy a good share of the life in these trees. They're flying insects. They're coming in. True story, one of the trees on the outside edge of the grove senses that they're coming, and he tells the rest of the trees to prepare. Now, when I say tells, they actually communicate chemically. They actually send a message to the trees saying, hey, bad guys are coming, get ready. And all the cottonwoods prepare this substance, which is poison, and the insects come, they eat, die, the cottonwoods go on. Now, chemical communication Again, the government's trying to figure out more about that. Here we have a picture of a corn crop. And they have discovered not too long ago that corn crops, how do you know when to water them? And it turns out the best way is to actually listen to them. You can't do it with ears, but if they have a special device, the corn crops actually cry out when they're thirsty. Really cool technology. So we've looked at those already. So as we get toward the end of this, we talked about how the brain is the ultimate computer that we're trying to get to learn more about. Psalm 64:9, all mankind will fear. They will proclaim the works of God and ponder what he has done. And now I'm just making the point in this presentation that science is doing this very thing. By the way, it's called bionics or biochemistry. So I've shown you this, I think, before. This is Johannes Kepler. And here's another quote from Kepler. Kepler discovered major laws. He discovered that we're on this mathematical ride around the sun. Anyway, here's what he said. The chief aim of all investigations of the external world should be to discover the rational order and harmony which has been impressed on it by God and which he revealed to us in the language of mathematics. Copernicus is the guy that discovered that the sun is the center of the solar system, not the earth, like the original church thought. And he said, the universe has been wrought by a supremely good and orderly creator. This is Leonardo da Vinci, a wizard, scientist, artist. You know, he had invented a helicopter in the Middle Ages. He says, human ingenuity may make various inventions, but it'll never devise any inventions more beautiful, nor more simple, nor more to the purpose than nature does, because in her inventions, nothing is wanting and nothing is superfluous, nothing is wasted. Okay, this is a picture of Galileo, and Galileo made some important, he's the first guy that discovered the telescope. And you can see here, he's trying to convince the church, some of the clergymen in this picture, he's trying to convince them that the earth, that the sun really is the center of the solar system, not the earth. And the church at that time thought it was the earth. Well, here's an experiment Galileo did. You probably have heard of this, but the Leaning Tower of Pisa, he went up on the tower and he dropped a small rock and a very large rock, and he dropped them at the same time. Do you know what happened?
They landed at the same time.
They did. That's right. It's an important principle. And on Apollo 15, astronaut David Scott repeated this experiment. I'm going to show you a little video on this.
Jim, we copied both solar wind and tennis or drum in the ETB.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. I have a good picture there. I've got
beautiful picture, Dave.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? It proves that Mr. Galileo was correct in his findings.
By the way, the reason he says he made a point out of the falcon feather. Is that year the lunar the device behind him there, the lunar module, was made, was called the Falcon. So that was kind of clever that they used the falcon feather.
Interesting.
So here's Galileo, and this is pretty amazing to me. Galileo made this quote, and I so very much agree with it. Mathematics is the alphabet with which God has written the universe. That to me is a perfect summary of basically it's kind of the theme of this whole thing. Why I said we're thinking God's thoughts after him, because God has given us this orderly, this universe that fits mathematical laws, and then we're just discovering it small piece by small piece. But some people have criticized him. They've said, "Oh, Galileo, yeah, his ideas are really kind of old." All right. So let's take a modern man. This is Eugene Wigner, and he won a Nobel Prize. Nobel Prize, top of the line. And look what he said. You know the statement that the laws of nature are written in the language of mathematics was properly made 300 years ago? It is now more true than ever before. Mario Livio, head of the science division of the Space Telescope Science Institute, and he said, "Is God a mathematician? For some inexplicable reason, mathematics does an extraordinary job of explaining the universe." One of my favorites, Sir William Bragg, said this about creation. He also won a Nobel Prize. If we once grasped the true significance of the Christian doctrine of creation, that in the beginning God made the heaven and the earth, then whatever we see or find in the earth must be a token of his purpose, his energy, his person. It's for this reason that science plays its part in our understanding of God. You know, by the way, today, don't you get the impression that science and religion, never the twain shall meet? And you just the opposite of what we're hearing here. If you have the right attitude and you're a Christian, science confirms what we learn in the Bible. Here's a Russian physicist, and he said it real simply. We know that nature is described by the best of all possible mathematics because God created it. This is Werner von Braun. Without him, we wouldn't have a space program. He was the guy that came up with all these rockets that we sent to the moon and so forth. He was a wizard when it comes to that. I didn't realize he was a Christian. And here's what he said. The more we learn about God's creation, the more I am impressed with the orderliness and unerring perfection of the natural laws that govern it. In this perfection, man, the scientist, catches a glimpse of the Creator and his design for nature. Okay. John Glenn, the oldest astronaut? Mm-hmm. When he went up on the space shuttle a few years ago, this is what he said to CNN. To look out at this kind of creation out here and not believe in God is to me impossible. It just strengthens my faith. I wish there were words to describe what it's like. So, just a short, this is kind of interesting. Different branches of mathematics. So, Berge from Switzerland, you notice his years, and a guy named Napier from Scotland. So they didn't know each other. They lived about the same time, and they both discovered an important part of math called logarithms that allowed seafarers to navigate more accurately and avoid obstacles. So my point is, they both discovered this at the same time. Coincidence? I don't think so. René Descartes, France, Pierre de Fermat, France. They came up with analytic geometry, which comes with calculus. This guy, he asked his dad if he could study geometry next year, and the father said, no, this year you will study Latin. Well, you know how a kid is. He studied geometry anyway, and he came up with the same geometry that all of us learned from a book. He had his names a little different, but so are these all coincidences? Here we have the two guys that discovered calculus, Newton from England and Leibniz from Germany. Coincidence? I don't think so. Kawa, Japan, same time as Leibniz in Germany, they came up with this topic called determinants in math. They didn't know each other. Coincidence? I don't think so. Carl Gauss and these other two gentlemen I don't have a picture of, Argand and Wessel, all came up with something called geometric representation of the complex numbers, which, by the way, has something to do with game technology, electronic games. And Bolyai in Hungary and Lobachevsky from Russia both came up with non-Euclidean geometry, which
They
had
kind of look the same.
What's that?
I said they kind of look the same.
Yeah, they have some similarities. Yeah. Well, as you can tell, they didn't have color photographs back then. Here we have Abel from Norway and Jacobi from Germany, and they both came up with. So these people from different parts of the world they discover math is not invented; it's discovered. Here on the left, did you guys ever see the movie A Beautiful Mind?
Mm-hmm.
That was a guy on the left, John Nash. And he and Ernie DiGiorgio discovered something about the same time. But most important of all is this Indian man, Srinivasa Ramanujan, grew up in a one-room house that really had a dirt floor in it, very poor, and had one math book to his name. And we found out later he discovered all the same math that the rest of the world has. Amazing coincidence? No way. So this is my quote. I believe that math is man's attempt at describing the order that God has placed into the universe. And just coming back to what, full circle. So you guys have seen now what, the two infinities, this one on the right here, and I just showed you thinking God's thoughts. We're not going to have a chance to get to the other ones. I thought if we'd have finished the third chapter, I was going to show you the divine proportion up on the top. You can view them. If you go to divinemath.com, there are presentations up for all of them. You're welcome to do that. So that's the presentation. Thank you for hanging in there.
Did you say that's at divinemath.com?
Yeah. Divine Math, one word, divinemath.com. Yeah, if you go there, I have a website there.
Okay, thank you.
So let's go back to our presentation. I don't know. I mean, just to see if you still have any questions or if you thought of some while I was doing the presentation. Chapter 3, final prep.
Just one question on the what do you call them, the switching networks?
Yes.
If you have this was problem 5 on 3.7, and I know we went over it in class and everything, but just, that I have the order straight. So we would do the parentheses, but when we're doing the network, we would put it in the order of the way the problem is laid out, right?
You could do it in the order of the parentheses too. The order is actually not critical. What is important is that the groups, like for example, P or not Q. Do you see how that's in its own little bracket up there on the top?
Yeah.
So that shows the parentheses, and then that, yeah, and then the second one here, this one in parentheses, not P or Q. That's this one right here.
Right.
But I mean, if that not P or Q was further up, that wouldn't matter as long as it was in the stack.
Okay. Okay. And then if we have I don't know if this is possible, but if you put a conditional in one of those statements,
yes,
then we just have to convert it to an or statement, right?
And how can we do that?
Using that hint?
That is correct. Way to go, Marilyn. Yep, that if P then Q is the same as what? Not P or Q. So excellent. If I gave, yeah, and actually I think that might be an extra credit on the test. So that's good stuff, Marilyn. Nice job.
Okay.
Okay, I can see we've been through this for a long time now. We should be in pretty good shape. That's my hope.
My hope too.
So that's what I'll do is I'll take your notebooks after the test is complete, and then I got to get busy on your tests and your notebooks.
Okay.
All right.
Okay, I'll see you Wednesday, everybody. Thank you for your.
All right.
Thank you for the extra time. Thank you.
You're welcome. Good night.
Good night.